Hello and welcome to lecture number 5 of the course Advanced Robotics Applications. Now, in the last class, what we discussed about was compound rotations. That is, if you are rotating a frame with respect to a fixed frame across multiple axes. For example, you can rotate about the fixed X or the fixed Y or the fixed Z. Then what we said, you can get the combined rotation matrix by pre-multiplying all the matrices. Okay, so something to remember is that when you're rotating about the fixed frame, you have to pre-multiply rotation matrices. After that, we looked at the homogeneous transformation matrix. That is, when an axis has been rotated and translated, then how do you express the coordinates expressed in a rotated and translated frame to that of the fixed frame? Okay, and we saw that the homogeneous matrix is a 4x4 matrix, which consists of the rotation part, it consists of the translation part, that is the difference between the origins, and then the perspective as well as the scale. Now, in the last class, we briefly looked at DH parameters. That is, when you're assigning access to a manipulator system, we see that you can relate one axis to another axis. That means if you're relating two axes in three-dimensional space, then at most you need 4 parameters. And these 4 parameters are called the link angle, the link twist, the offset, and the link length. Okay, so today I will very quickly go into the DH parameters again, explain this very quickly, and then we'll see some examples of how to assign DH parameter tables and make the DH parameter table for different manipulator systems. Now, with the DH parameter table, we can very quickly make the transformation matrices from one axis to another axis, and when we multiply them out, we can get the final position orientation of the end effector with respect to the base frame. Okay, so we'll very quickly revise about DH parameters, that is how to assign access to a frame or rather assign axis or frames to a manipulator system at every joint, and then how to make the DH parameter table. So very quickly I will revise before we proceed. So we have let's say we have a link here. It can have any shape. In three-dimensional space, a link can have any shape. So I'm just drawing a link which is having a little strange kind of shape maybe, but then this is basically to explain that the link can actually have any shape. Okay. Now, what we see is that we assign our z-axis first. The z-axis is the axis of rotation or translation. So this is my z-axis. I can call this zi minus 1. And this is my next z, which is my zi axis. Okay. Next, we assign our x-axis, which is the shortest distance between, well, let me draw this axis here, which is the shortest distance. So if I keep this is the shortest distance, then I say my xi minus 1 is here. Okay, and the next one, the xi is on that frame. Okay, so next we have 4 parameters which are called the DH parameters. So what we do is I rotate the zi minus 1 axis by an angle alpha, and I make it parallel to the next axis. So I just rotate it like this by an angle alpha, so that these two become parallel. So we have a parameter alpha, which is the angle. Okay, so this is the angle between the z-axis measured along the x-axis, measured along the x-axis. Okay, so this is my first parameter, which is called the twist or the link twist, which is called alpha. Next is the distance a, that is I move the origin from here to here, okay, by a distance a, and a is called the link length. So this is called the twist or the link twist. This is called the link length. Okay, this is called the link length, and it is the distance between the z-axis measured along the x-axis. Okay, so this is my second parameter, which is the link length, which is a. Okay, so my frame has now come here, and this is my xi minus 1. This is xi minus 1, and this is my zi minus 1. Okay, now we see that the x-axis are still not aligned, or they are not parallel, so I rotate the x by an angle theta. Okay, so alpha a theta is called the link angle, and the link angle is this is called the link angle. Okay, this is called the link angle, and this is the angle between the x-axis measured along the z-axis, okay. So now my xi minus 1 has come here. Now the xi minus 1, this and this are parallel, okay. Now we still see that there is a distance between the origins, so I move the origin from here to there, and now the zi minus 1 is here, xi minus 1 is there, so both the axes are aligned. So this is my d, which is called offset, and it is equal to the distance distance between the x-axis measured along the z-axis. So we have got 4 parameters here. So alpha, a, theta and d and theta. So these are called the 4 DH parameters, okay, and this is how we measure them. Now let's look at an example of now what is the point of doing it this way? The point is that if you assign axes this way, you have only 4 parameters which relates any frame in 3-dimensional space to any other frame in 3-dimensional space. Otherwise you need 6 frames, because a body in a freely floating body in space can have 6 degrees of freedom, 3 translations, 3 rotations. So it would appear that you need 3 rotations and 3 translations, you need 6 transformations. But if you do it like this systematically using the DH method of doing it, then basically you need only 4 transformations. That is the advantage of doing this. Okay, let's proceed and see how do we use this and what is the use of this. So let us proceed and see the use of this. So let us look at a very simple manipulator system. Okay, so this is a very simple manipulator. This is one axis, this is the second axis, and that's my third one. Okay, now first thing is that this is a 3R manipulator, 3R robot or manipulator having 3 degrees of freedom. Okay, so we understand that this has 3 degrees of freedom and the 3 revolute joints, and it is also planar. Please note. So the first thing that you should do when you look at a manipulator is that you should try to figure out whether it's what is it moving in 3D, is it moving in 2D. Now this one is moving in, it's planar. What is the meaning of planar? It basically means if it moves, it can at most come here, okay, or go this side, okay, but it cannot come out of plane. That's what I mean by planar. It has to be on this plane, okay. So that is the meaning of the word planar that I used here. Okay, now let us say this is my link length L1, this is my link length L2, okay, this is my link length L3. Okay, now the first thing as per DH we say we assign our z-axis. So the z-axis is axis of rotations or translations. Now in case of this is a 3R, means 3 rotation joints, so the z-axis is pointing outward. This is z0 and z1. z0 is the fixed frame which is not moving, and z1 is the first axis which is fixed onto the first axis, okay, or to the first link. This is my z2, this is my z3. Okay, now x0, x is the shortest distance, so this x0 can be anywhere, is the reference frame. The next x will be along the shortest distance, so it is there. So if z1 and z2 are parallel, then the shortest distance is between them, which is x1. This is x2 and that is x3 now. Okay, so if you say the angle, this is my theta 1, that's my theta 2, and that's my theta 3. Okay, so this is how we assign our axis. Z-axis is the axis of rotation translation. X is the, or let me say x is shortest distance between z. Okay, shortest distance between z's. Okay, if z's are not intersecting. If they're intersecting, then it is perpendicular to the z's, then it's perpendicular to the plane containing the z's. I'll just come to that shortly. Okay, so I have put my x and my z-axis, and now I have to make my DH parameter table. So let's make the DH table. So DH table, we are making it here. So there are 4 parameters: a alpha, d, and theta. Okay, these are my 4 parameters. Okay, now this is 1, 2, and 3. There are 3 axes here. Now to understand, this is the relation between 1 and 0, 2 and 1, and 3 and 2. Okay, that is the meaning of in terms of frames. Okay, so if I see in terms of frames, then this relates, the first row relates frame 1 to frame 0, the second row relates frame 2 to frame 1, and the third one relates frame 3 to frame 2. That's the meaning of this row. Now when you're doing it for the first time, it also is a good idea to write down what this means. For example, A is the distance between, so this is distance between the z-axis. Alpha is the angle between the z-axis. This is the distance between x-axis, and that is the angle between x-axis. Okay, this will make it a little bit clearer that what is it that we're writing. So the first parameter, A, is the distance between the z-axis of the frames 1 and 0. Now the frame 0 and 1 are the same axis, so there is no distance between them, so it is 0 because they're intersecting at a point. Now if you look at the angle between the z-axis, again they are the same axis, so it is 0. Okay, there's no angle between them, it's the same axis. You can see 0 and 1 are here. Okay, now what about D is the distance between the x-axis. Now the x1 and x0 are intersecting at that point there now. So again there is no distance, that is 0. Now theta is the angle between the x-axis. So when this manipulator moves, what changes? So let me say this manipulator is moving, it has gone here now. Okay, suppose it is like that. What has changed? This angle has changed. The angle between the x-axis has changed. So this is the variable which is called theta 1, or that is the variable which is theta 1. Okay. Next is the parameter between link for the second joint with respect to the first joint, in this case frame 2 to frame 1. Now where is frame 2? Frame 2 is here. Okay. Now look at the z, that is A. Now A is the distance between z. It is the distance between z2 and z1. Okay. So what is the distance between z2 and z1? It is L1, the link length which is given here. Okay. What is the angle between the z? The z2 and z1 are parallel, so the angle is 0. What about the distance between the x? Now x1 is in this direction, like this means this direction. Okay, and x2 is in this direction, so they are intersecting at that point there. So which basically means that this is no angle, there's no distance between them. Now when the link 2 moves, okay, when the link 2 moves, what will change? Link 2 will come here. Okay, so what has changed? This angle has changed, so the variable is theta 2 there now. Okay, so what is changing is the variable theta 2. Now what about the third one, that is third frame to second frame? So where is the third frame? Third frame is here and second frame is here. So if you look at A, which is the distance between the z-axis, so there is L2, which is the distance between z3 and z2. Then what is angle alpha? Alpha is the angle between z3 and z2, which is 0 because they are parallel axis. What about the distance D, that is the distance between the x-axis? Now x2 is this side, that is my x2 if I extend, and this is my x3, so this is my theta 3. So there is no, they're intersecting at a point, so there is no distance. And when theta 3 moves, what will happen? This will come here. So what will change? This angle will change. So my theta 3 is the variable there now. So this is what I call as the DH parameter table. Okay. Now what is the function of the DH parameter table is that I need to make my transformation matrices T0 to 1, T1 to 2, and T2 to 3. Then I'll multiply these ones out and I'll get T0 to 3 is equal to T0 to 1 into T1 to 2 into T2 to 3. Right? Now using this these parameters, what we will do is we'll make the transformation matrices. And once we make the transformation matrix, I'm going to multiply them out. Okay? So this is one example. Now you need to practice this by yourself, otherwise it can get a little, it is not confusing once you understand, but you need practice to really understand this carefully. Okay, so I would suggest that please do practice this properly. Now we said that there is an exception in the sense of the z-axis, that the z-axis, in case where the z-axis are not intersecting, then there is no shortest distance between them. In that case, what will happen is the x-axis will be perpendicular, will be out of the plane of the z of the plane containing the z-axis. Okay, so what I'm trying to say is that here when I said the z-axis is the rotation or translation axis, the x-axis is the shortest distance between the z's, but that is provided the z's are not intersecting. So if z's are intersecting, then the x-axis is perpendicular to the plane containing the z-axis. I'll give you an example so that it makes it clearer. So let's look at this example here now. This is a manipulator again. Okay, so this is one. This is one. Let me change the color. This one link. This is another link. Okay, so this is another link, and that's a third link which is here, which is this one. So that's the third link. Okay, so there are 3 links of 3 different colors. Now this manipulator is 3 degrees of freedom. This is also 3 degrees of freedom, 3 DOF, but it has 2 revolute joints and 1 prismatic joint. What are the revolute joints in the prismatic joint? Let's try to understand this carefully. The first axis is this one. It can rotate about that axis. Okay, so it can rotate about this axis. Okay, so this is my first axis. Let's say that's my first axis. Next is there is a prismatic axis. The prismatic axis means it can move in that direction. So this link, which is marked with violet color, which is moved, can go front and back. So this can come back like that. Okay, so this one can come back. Okay, so this link which is going through there can come back. So this one can come here like this now. Okay, so this full link can come back like that. Okay, and that is the prismatic distance. So that is a prismatic variable. So this is moving in a straight line. Either it can move this side or it can move back in that side. Okay, so that is my second variable, or the second joint. Now the third one, which is the red color, is a rotating joint again. So this one can rotate about that. It's like a roll motion, it can rotate about that axis. So where are the 3 axes? Let us put the axis. First we understood that there are 2 revolute joints and 1 prismatic joint. Then we have to put our z axis. Z axis is axis of rotations or translations. Okay, so this case, where is the first one? Let me put my z axis like this. So z0 and z1 come there. Axis of rotations. Next is axis of translation. This is my axis of translation. Okay, it is translating about this axis. Let me bring it down here. It is translating like that. So that's my second axis, z2. Okay, so that is the translating axis. z3 is the rotation axis here again. That's my z3. Okay, so that was simple. Z-axis is the axis of rotations or translations. In this case, there is 2 rotations and 1 translation. Okay. Then what we do is we put our x-axis. Now x-axis is, in this particular case, what we see that x-axis is the shortest distance between z's. Okay. But if z's are intersecting, so if z's are intersecting, then x is perpendicular to plane of z's. Okay, so this means that if the z-axis are intersecting, okay, then we say that the x-axis is perpendicular to the plane containing the z's. Now let's look at this manipulator. Z1 and Z2 are the same axis. So what we see here is Z0 and Z1, same axis. Okay, they are the same axis. However, Z1 and Z2 are intersecting axes. Now if they are intersecting axes, then there is no shortest distance, and that is where the problem is. And that is why we need to use this clause, that if the z's are intersecting, then x is perpendicular to plane containing the z's. Okay, so now let's mark our x-axis. So Z0, Z1, I'm going to mark x0, x1 and x2. Now we know that Z2 and Z1 are intersecting, okay, and hence x2 has to be perpendicular to the plane containing the z's. What is the plane of z? This is the plane containing Z2 is this side, Z1 is that side. So this is the plane of z's. Okay, so x2 is perpendicular to the plane containing the z's. This is the condition here. And because x2 is this side, I put x1, x0 and x1 also this side. I put x0 and x1 also here. Okay, and now I put x3 this side. Okay, so we have got x1, x0, x1 and x2 and x3. Okay, but here we have to be a little careful because the z2 and z1 are intersecting. Okay, now I can write the DH parameter table of this one. Let me say that the variable is theta1 is the variable here. This distance, which is a variable here, is d2, and theta3 is the variable there. Okay, d2 is the translating variable. Okay, and there is a distance, let me say, from here to here, there is a distance which is L2. Okay, I hope you can imagine that. Now please note that Z1 and Z0, Z1 are on link 1. Okay, Z2 is on link 2. and Z3 is on link 3. Okay, so when link 2 is moving, the frame Z2 is actually moving with the link. Okay, so it can go this side or it can go this side. Okay, and that is how the variable D2 changes. Okay, I hope you can follow that. Or let me just draw it here to explain this better. This is something that you need to understand. So this is my link 1. Let me mark it as link 1. Then link 2 we have is the red color. Let me say this is red color. It is here. It is going through like that. Okay, and then we have link 3, which is here. That's my link 3. Okay, now the green axis, which is marked, is here on link 1, is Z0, Z1. It is fixed on the green link. The red link is the second axis. This is my Z2. Now Z2 axis is fixed. So if this is my Z2, so this is my Z2. This is fixed on the red color link, which is link 2. This is link 2. Okay, so when link 2 moves, maybe link 2 will come like this. You know what will happen? This will come this side. Okay, this will come this side, like that. Okay, because link 2 has moved. So when it moves, what will happen is the origin also will move because it is fixed on that link. Red color origin is fixed on the red link. So when it moves on the left side, this origin will also come this side. So it has come here now. I hope you understand that. Okay, and what about the x-axis? So my x-axis is here. So x0, x1 and x2, and x3 is here. Okay, so when the z link is moving on the left or the right, what is happening? It is carrying with it the origin and the frame 2. So x2 can come this side because z2 can be here. So when the link is moving to the left, when the second frame is also moving with the link. Okay, so what is happening is going this left side, like the way I have drawn it. Okay, so now there is a distance between here and here. Let me say there is a distance of L2. Okay, now let's write the DH parameter table. Okay, now in the DH parameter table, again we have A, alpha, D and theta. So A is the distance between z-axis. This is the angle between z-axis. D is the distance between x-axis, and this is the angle between the x-axis. Okay, we have 3 degrees of freedom, 1, 2, 3, which has 3 degrees of freedom manipulator having 2R and 1P joint. Okay, so the first is the frame relation between 1 and 0. So this is 2 and 1, and that is 3 and 2. So what we see is that the distance between the z-axis for 1 and 0, this is the same axis, so there is no distance there. Again, z0 and z1 are the same axis, so there is no angle between them. Okay. What about the distance between the x? z0 and z1 are the same axis, so basically there is no distance between them. And what you see is that when this rotates, what changes? The angle between these two will change. So z1 can come like that. So I hope you can imagine that this is the rotation theta 1. So x1 can go this side or x1 can go this side. That's my theta angle. Okay, and they're intersecting at a point, so there is no distance between them. So my variable is theta 1 here. Okay, next what we see is that for frame 2 and 1, now let's look at frame 2 and 1. Okay, frame 2 and 1. So when frame 2 moves, what happens? It can go towards the left side or the right side of the 0 frame. Okay, so it can go on the right or the left because it's a prismatic joint, and the variable we say is d2. Okay, so what is the distance between the z-axis? Now z1 and z2 are intersecting, so there is no distance between them. Okay, what about the angle between them? Now we see that z2 is on this side and z1 is pointing upward, whereas z2 is horizontal, so there is 90-degree angle there. Okay, so what is the angle between z1 and z2? So z1 is rotated by 90 degrees clockwise and it becomes z2, so it is a minus 90. So we say counterclockwise rotation about x-axis. Okay, so we say that if it is a clockwise rotation, then we say it is minus. If we say counterclockwise rotation, we say it is plus. Okay, please note this. This is the basic convention. Okay, now what about so it's a minus 90. What about distance between x? This is the distance here. This is what we need to note here. So x1 is here and x2 is here. So when it moves, the distance d, this is the distance d actually. So there is a distance between the x1 and the x2. because when the red link moves, it carries with it the frame 2. So the distance between x1 and x2 will change. Okay, and that is this one, which is my d2. There is no angle there, so it is 0. Okay, please be careful of this one because it's a prismatic joint. Next, what we see is that we talk about the relation between the third frame and the second frame. Now, what is the distance between the z-axis? Now, the z-axis are in the same direction. This fellow z is in that direction. That's my z3. Okay, so they are in the same direction, so there is no distance between them. What about the angle between them? Again, there is no angle between them. They are in the same direction, so it's 0. What about the angle between the distance between the x? Now, we can say there is a distance of L2 between the x-axis, the way I have drawn it. Okay, so L2 will come right till here. So, yeah, so that will come till there. So, when the x goes to the right or the left, what will change is this d. Okay, and L is a fixed length. So, if I were to draw the this is a little confusing, so let me draw it here again. So this is the third link, this is the second link, and this is my frame, and this is my, so I fixed my origin here. I fixed my origin of 2 here. This is my z2. Okay, and this is the z3, this is x3, this is x0, x1, x2. Okay, now when the red link moves to the right or the left, this distance is my L2. This will not change. But the distance between frame 1 and frame 2 is going to change. Okay, that means the distance between x1 and x2 is going to change. Okay, that is my d. So please note that carefully. Again, this can rotate about this axis, and that's my variable theta 3. So there are 3 variables here. Theta 1 is a variable, d2 is a variable, and theta 3 is a variable. So in the case of prismatic joint, the distance is a variable. In the case of a revolute joint, an angle is a variable. Okay. Now, what is the use of this? The use of this is that I need to find this transformation matrices. Okay. Now, if I go back a little bit more, we said that there are 4 parameters, and each of them is a transformation matrix variable actually. So if I have 4 transformation matrices and I multiply them out, I can get a generalized matrix. And from the generalized matrix, what I can do is I will take each row of the table, of the DH table, put it in the generalized matrix and get the transformation matrices. Okay, I'll explain as we go along. So this one is a rotation. Okay, this is a rotation. This is a translation. This is a translation. That's a rotation. So there are 2 rotations and 2 translations involved. Okay. So now what we will do is I will take this manipulator again and write down the transformation matrices. Okay, so let's go back here and write down the transformation matrices. Now I said that you have A, alpha, theta and d. So if I multiply all these matrices together, I get a generalized matrix which takes me from I minus 1 to I. Okay, which can be written this way. So this generalized matrix can be written this way. So this is cos theta minus sin theta 0a, then it is sin theta cos alpha minus sin alpha d, sin theta sin alpha cos theta sin alpha cos alpha d, and this is 0 0 0 1. Okay, this is the generalized matrix which relates any frame, the ith frame to the I minus 1th frame, to the previous frame. Basically, that's what it means. So if I is 1, then this will be 0. If this is 2, that will be 1. So it relates the next frame to the previous frame. Okay, this is what is the meaning of this. Now, what is the use of this is I can take each of the rows of the DH table. I can take this 0 0 0 theta 1. This relates axis 1 to axis 0. So I can take 0 0 theta 1, put it into that matrix. Okay, I can put it into this matrix and get my first transformation matrix for that manipulator. I'll draw it again and explain. I can get it as what will it be? Cos theta minus sin theta 1 cos theta 1. This is 0 0 1, that is 0 0, and this is 0 0 0, this is 0 0 0 1. Okay, so if you go back and remember, if you remember what I had written in terms, it is 0 0 theta 1. So there's only one variable theta 1. This is 0 0 0 and theta 1. So if I take it and put it in this matrix, what I'll get is, so theta 1 will come here, theta 1 will come here. Okay, so what I'm getting is cos theta 1 minus sin theta 1 cos theta 1, because that's the only variable. Alpha is 0. Okay, and a is 0, so that's a 0 there. D is 0, D is 0, so this is 0, 0, and it's a rotation about the z-axis, so this is a rotation about z-axis. So I hope you can correlate that this was a rotation about the z-axis. Okay, so this is my first matrix. Okay. So in the case of a computer program, how the computer program for a simulation works. So when we'll be talking about the experimentation and the simulation part, how do you simulate a robot? You will not write by hand. Okay, it's very long and the expressions become very long. Okay, so what is done is the DH param, the simulation program basically has this matrix, the generalized matrix. So it basically, and you are supposed to enter the DH parameter table, or it can find out the DH parameter table from the structure. So from there, it will take one row. This is a row. So this can be looked upon as a matrix. So from this matrix, it will take one row at a time, put it in the generalized matrix, and get this transformation matrix. Then it will take the next one, get this one, then take the third one, get this one, then multiply all of them out and get the position and orientation with respect to the end effector. Okay, I'll give a better example or a simpler example, and then we'll proceed. So I hope you understood where I got this matrix from. Okay, so there are 4 transformations. If I multiply all the corresponding matrices, okay, what I'll get is this generalized matrix, which contains those 4 parameters only. Okay, let's proceed and come back to this very simple case of 3-link manipulator. Okay, so this is 3R, 3 degree of freedom manipulator. Okay, so I'm repeating, but please do pay attention on this, although I'm repeating. So Z0, Z1 is here, Z2 is here, is the axis of rotation, Z3 is there, X0 is here, X1, X2, and X3. This is link L1, link length L2. Okay, the DH table which I had written, so A alpha D theta, I'm writing it fast, 1, 2, and 3, it is 0, 0, 0, theta 1, it is L1, 0, 0, theta 2, it is L2, 0, 0, theta 3. Okay, this is the DH parameter table. Okay, the same one. I hope you can go back and you can verify how did I get this. So what I'm interested in, I want the position orientation of the third frame with respect to the 0 frame now. So that means that I take one row at a time, okay, and put it into the generalized matrix, which is this one, and then I multiply all the matrices together. The other way is, you have studied about rotation matrices. I explained rotation matrices in the last 2 classes. So this is a rotation about z-axis. Now you know the rotation about z-axis is this matrix. Okay, cos theta minus sin theta, cos theta. It is 0, 0, 1, 0, 0. This is the structure because it's a rotation about z-axis. So the rotation matrix will have this one. Okay, now in terms of the T matrix, which is a homogeneous matrix. So let's go back here again. This is a homogeneous transformation matrix. This part is the perspective. Okay, this is the scale. Okay, this is the distance between origins. Okay, and this is the rotation matrix. Rotation is about z-axis. So if you look at the structure, if it's a rotation about z, this is a rotation matrix. It may be about any axis. That's why it is having all the elements. But if it is a rotation only about z-axis, then it will only have this elements. That's a rotation about z. Okay, so it will be rotation about z. It will be 0, 0 there. Okay, so in this case, let me write down the first matrix. The first matrix is written by so T 0, 1. T 0, 1 is my first matrix, which is cos theta 1. I'll write it in short as cos 1 minus sin 1. Sin 1, cos 1, 0, 0, 1, 0, 0. This is 0, 0, 0. And this is also 0, 0, 0, 1. That's my first matrix. Okay. The second matrix is T 1 to 2. Okay, so let me take the second row and put there. What will I get? What is the variable? Theta 2 is the variable. So theta 2 is the variable. So cos 2 minus sine 2. Sine 2 cos 2, that is 0, 0, 1, 0, 0. This is 0, 0, 0, that is 1. Now here we see, if I go back, there is a length L1. So where will this length L1 appear? It will appear here. Okay, so this is my length L1, D is 0, so that will become 0. Okay, so my length will appear here as L1, that is 0, 0, 1. Okay. Now, what about the third one? Let me write the third matrix here. So this is my third matrix, T 2 to 3. This is my third matrix. So third matrix, I take the third row from here. Variable is theta 3, so cos 3 minus sine 3 cos 3, 0, 0, 1, that's 0, 0. This is always 0, 0, 0. Then it is L2 is there, 0, 0, 1 is there. Okay. Now what am I trying to do? I'm basically trying to find the relation between the third frame. So T0 to 3 I'm trying to find, and that is equal to T0 to 1 into T1 to 2 into T2 to 3. So I need these matrices. Once I get these matrices, I can multiply them out. Okay, then I'll have to multiply all these three matrices out now. So let me multiply this into that. So if you multiply these two matrices, you know how to multiply matrices. So so this row into this column, what we'll get is cos 1 cos 2 minus sine 1 sine 2. Okay, so the first term will become cos 1 cos 2 minus sine 1 sine 2, which is equal to cos theta 1 plus theta 2. In short, I will write this as cos 1 2. I'm writing in short. Okay, this is the first term. This is term number 1. So what we'll get when we multiply T01 to T02. So I'm multiplying these two now. Okay, these two. That means these two matrices are multiplying. So when I multiply those two matrices, what I will get is cos 1 2 cos 1 2 minus sine 1 2 sine 1 2 cos 1 2 0 0 1, that is 0 0. This is 0 0 0, and what I will get here is L1 cos 1, and this will become L1 sine 1. That will become 0. That will become 1. Sorry, the other way around. 2 to 0. Now I multiply this with this one. Okay, the third one. Now I multiply with this one now. Okay, which is this matrix. Now if you multiply, what would you get? This into that. Okay, what will it be? Exactly the same here. Cos theta 1 plus theta 2 plus theta 3. So what I will get is cos theta 1 2 3 minus sine 1 2 3. Then sine 1 2 3 cos 1 2 3. Okay, 0 0 1 0 0. This will be 0 0 0. Now here what we'll get is cos 1 2 into, so it will become L2 cos 1 2 plus L1 cos 1, and L2 sine 1 2 plus L1 sine 1. This will become 0. That will become 1. Okay, so this is 3 to 0. Okay, please multiply them out by yourself and you can make out. Okay, so now what we see is that we have multiplied all the matrices out, and what we are seeing is that this is the way you write, or this is how a computer program would operate. So what it will take is, it will take each row of this, put in the generalized matrix, get the corresponding transformation matrix, and after it gets all the transformation matrices, it will multiply them all out and get the relation between the last frame and the first frame and the zero frame now. So you can imagine that this is for a 3 degree of freedom system, but a real robot will have about 6 degrees of freedom, or could be even more, could be 7, 8, 9, 10 degrees of freedom. So if you have to do it for a 6 degree of freedom manipulator system, it will have 6 matrices which you have to multiply, and it is not difficult, but then expressions become very long and there is a chance of making a mistake. So what is done is a computer program is used, and the computer program would look at the DH parameter table, and from the DH parameter table it will basically take each row, put it into that generalized matrix, and then get each of these matrices and then multiply them out. Now, for a computer to multiply matrices is very easy. Now let's look at the interesting and the important part is, in case you're wondering, that I wrote down all this, especially this matrix I just wrote down. Okay, maybe I by-hearted everything, or I have something written down with me, beside me, and I'm just copying. Well, I'm not copying. Okay, I just wrote all of this myself only. just now on the screen. Okay. Now, if you think a little bit, one question that may come to your mind is that if you have a 10 degree of freedom system, this matrix is going to become very, very long, and it'll have a lot of terms. Okay. How do you know it is correct? Or what I wrote here, is it correct? If you are asking yourself that question, that I have written this down, and is this correct? Or could I have written this down without doing all these computations? So if I ask you to write the relation, if I show you this manipulator, and I say that what is the relation between the third frame and the zero frame, just by looking at this, can you write that final matrix? Because we said that there is a structure in this matrices. Okay, so if you understand the physical structure of this matrix, then you should be able to write it very easily, right? So let's look at this. This is a homogeneous transformation matrix which consists of 4 parts. This is always 0, 0, 0. This is always 1. So nothing there. Okay, so all the matrices you see is 0, 0, 0, 1, 0, 0, 0, 1. It can't be anything different. Now, in the case it becomes different in a program or somewhere, you immediately know that there is a mistake. It cannot be. Okay. Now, this is the rotation matrix, this part. And if you look at the structure, it is saying that it's a rotation about z-axis. Okay, or let me explain it. Let me draw it and explain it, because this part is very, very important for us to understand. Okay, let me draw it a little bigger so that it becomes clearer. So what I did is we put z01 here, z2, z3. This is my x0, this is my x1, this is x2, this is x3. Okay, now in my and then this was my theta 1, that's theta 2, that's theta 3. Okay, so the matrix T0 to 3, sorry, the other way around, 3 to 0, what I had written some time back was cos 1, 2, 3. This means cos of theta 1 plus theta 2 plus theta 3. That's the meaning. Minus sine 1, 2, 3. This is sine 1, 2, 3. Cos 1, 2, 3. That is 0, 0, 1. That is 0, 0. Okay, this was 0, 0, 0. And this one was 1. And this term was L1 cos 1 plus L2 cos 1, 2. And this was L1 sine 1 plus L2 sine 1, 2. That is 0. Okay. So the question is, could I have written this matrix like the way I did it now? I just drew this and I wrote it there. I did not do any computation. So the question comes, is it correct, and how did I write that? Okay, so let us look at it this way and try and understand. There are 4 parts of this. This part is perspective, it's always 0. This is always 1. So if you ever happen to see a matrix, or you happen to compute a matrix where this numbers change, you immediately know that there is a mistake. Now let's come to the rotation part. This is the rotation part. Now in this manipulator system, the z-axis is the axis of rotation or translation. That means these are the rotations, and the rotations are all about z. Okay, so the structure of this part, the rotation part, will have the structure of the rotation matrix of z theta, which is equal to cos minus sine cos 0, 0, 1. Okay, so this is the structure. You can see it's still having the same structure. It's a rotation over z. Okay, that's the structure. What about this? This is the total rotation that the axis 3 has with respect to, so the x-axis of third frame with respect to the x-axis of the 0 frame. Okay, that is the total rotation it has. That's the meaning of this. So if you look at it here, our z3, where is our x3? My x3 is here. That's my x3 axis. Where is x0? x0 is here. Okay, so what is the relation or the rotation of x3 with respect to x0? So first x0 is rotated by theta 1. So it went here. Okay. Then it is rotated by theta 2. It went there. Okay. Then it is rotated by theta 3, and then it went there. I hope you understood that. So first there was the rotation of theta 1, then rotation of theta 2, then theta 3. That's how this term cos theta 1 plus theta 2 plus theta 3 came. Okay, that means this is a total rotation that took place here. Or what is the relation between the x3 and the x0? So it is the sum of theta 1 plus theta 2 plus theta 3. And so it is theta 1 plus theta 2 plus theta 3. That's how that came. Okay, so I could have just written it straight only, because the total rotation is what is coming there. Okay. Now, so that's the first part. So the rotation part is correct. Okay. Now, what about the this part? Now that part is, we said APB ORG, or the distance between the origins. Okay, it's the distance between the origins. Now, if I see the distance between the origins, then my third origin is where? My third origin is here. That's my third origin. The black color is there. Where's the zero origin? It's here. Okay. So if this is my x-axis, x0, this is my y-axis, y0, and this is my z, z0. Okay. So in this axis system, if I see the relation of the distance of the origin of 3 with respect to origin of 0, then this fellow, what is the distance in the x direction? So the x direction is this much, which is L1 cos theta 1. What is this one? This is equal, this much is equal to this much, which, if this is theta 2, this is theta 1. So this is equal to L2 cos 1 2. Okay, I hope you understood. So what is the total? This total distance from here to here is equal to L1 cos 1 plus L2 cos 1 2. Okay, and that is L1 cos 1 plus L2 cos 1 2. Okay, now if you look at, so that is the distance in the x direction. The distance between the origins is this one, which is L1 cos 1 plus L2 cos 1 2. Now if you look at the, let's look at the other one. Let's look at in the y direction. In the y direction, what is the distance between the origins? It is this much. How much is that? That this is equal to this. So it is L1 sine 1. Okay, and what is this? This is equal to L2 sine 1 2. Okay, this is L2 sine 1 2. Okay, so what is the total distance? This plus that. So the total distance is L1 sine 1. So the total distance is L1 sine 1 plus L2 sine 1 2. Okay, and that is here. So this is the distance in the x direction, that's the distance in the y direction. Now this is a planar manipulator, so z cannot move, so z direction, it cannot move in the z direction, so it is 0. Okay, so I hope you realize that we could have looked at this manipulator and then written out the answer also. Okay, so this is what is interesting here, is that once you understand, okay, how the frames are moving, or you can correlate physically what an axis means, especially in the experimental system, because this course is about experimentation. So we'll see actual robots which are moving. So when it moves in space, how do you correlate the end effector position orientation with the base frame? Once this is clear, you can do it very, very easily. Let's look at one more example before we stop today. So let's look at one more manipulator here. So this is another manipulator system. Okay. So this is one link. That is a next link. Let me change the color. So this is another link. Okay. Now, first of all, what we need to do is to understand that how this moves. So when this is moving, we need to figure out how it is moving in space. Well, then we can put our z-axis. So it can rotate about this axis. Let me say it can rotate about this axis. So that's my first z-axis. So z0, z1 I put there. Okay, it can rotate about that axis. Number 2 axis is this one. This can go up and down, so it can rotate about that axis. So that's my z2. The third one is it can rotate about this. That's my z3. Okay, so I have put my z1, z2 and z3 axis. Now z2 axis could have been here also, but I'm just simplicity, I'm putting it here. Okay. Now what we see is that here also, now I have to put my x-axis. The same problem comes, z2 and z1 intersecting. So x has to be perpendicular to the plane containing them. So z0, z1, z2. This is the plane of the z's. So x2 is perpendicular to that plane. Okay. Now let's see, there is a distance. Maybe we can call this distance. So there is a distance here. So let me mark the distance here. So the distance here is that distance is there. Let me call it A2, and there is a distance here. Let me call it D2. Okay, that is this distance. Okay, so now the first 0 and 1 frame origin is here. Second frame origin is also here. I could have taken second frame origin here, but just simplicity, I'm taking it here. Okay, and third frame origin is here, so I'm saying my x3 is this side. Now let me make my DH table. So let me make my DH table. So A alpha d and theta. So I have 1, 2, and 3 axes. So A is the distance between the, so we can again write down here is the distance between the z axis. This is the angle between z. This is the distance between x, and this is the angle between x. Okay, just to remember how we get this number. So distance between, so 0 and 1, 1 and 2, 2 and 3. So the 0 and 1 z-axis are the same, so it is 0. Now what is the angle? It is 0. The distance between the x-axis is also 0. This is theta 1. Now we see z2 and z1 are intersecting, so there is no distance, is 0. Now again there is an angle of 90 degrees, so it's minus 90 degrees. Okay, and then what is the distance between the x-axis? The x-axis, there is no distance, and this is again rotation axis, which is 2, which is theta 2. Okay, what about the third one? Now look at the third axis. Z3 is here. Now this Z3 is here, Z2 is there. Okay, so what is the distance between them? It's A2. This distance, A2. Okay, they are parallel axis and the distance is A2. What is the angle between them? There is no angle because they are parallel. What is the distance between the x-axis? Now x3 is here and x2 is there, so there is a distance here now. It's like saying this has moved from here to there, then it has moved like that. Okay, so this distance is there. This is my d2. So this distance becomes z2, and this is theta 3. So this is 3 degree of freedom, 3R manipulator. Okay, so today's class, okay, so today we'll end here. Today we discussed about DH parameters, and using DH parameters how we can make the various transformation matrices. And after making the transformation matrices, we need to multiply all the matrices. And after you multiply the matrices, you will get the final matrix, which will give you the relation between the end effector position and the end effector orientation. Now, from control point of view, the controller would need to know where is the end effector position and orientation. Because when you're doing a task, for example, I have a pen and I have to go and pick up this pen. Okay, I will need to know the position orientation of the pen before I can go and pick it up. So the final matrix is the one that the controller uses to control the manipulator to take it to some desired position and orientation. So today we'll stop here and continue in the next class. Thank you.